Hello everyone. In this video, I'm gonna tell you how to solve the question number B and 0 and some big and 0 some big of Codeforces round 716 div 2. First, let's understand the question. Baby Badawi's first words were and 0 some big. So he decided to solve the following problem. Given two integers n and k, we have two integers n and k. Count the number of arrays of length n. This is an array of length n and such that all its elements are integers between 0. These elements are between 0 to 2k minus 1, which is this is inclusive, and bitwise n of all its elements. So all, if we bitwise this is element 1, index 0, index 1, index 2, index 3 till n minus 1. If we use a bitwise n operation on all these elements, the answer would be 0. And sum of its element is largest possible. So yes, so sum is largest max. Since the answer can be very large, it print its remainder when divided by 10 to the power 9 plus 7. So answer should be equal to answer mod 10 to the power 9 plus 7. Okay, this is a input test case, first test case, then n and k, n and k, n and k. Now test is n and k, then output the number of arrays that is possible. So here, before moving on to the solution, you need to have some prerequisite knowledge like bit magic, bits operation, binary operation. You need to know n operation, how to do bitwise n. Then you need to know how to convert a number to its binary representation. Then you need to know permutation and combination. All these things are applied in this problem. So first, let's understand the array. Some conditions doesn't matter. Few conditions are only matters here. Let us consider the first test case. It is saying n equal to 2 and k equal to 2. So here need to print the number of arrays that is of length n equal to 2 that is possible. N equal to, so this is an array of n equal to 2. So how many more such arrays are possible whose length is 2? Okay, and each element of all these arrays should be between 0 to 2 to the power k minus 1. That is 2 to the power 2 minus 1. So 0 to 2 to the power 4 minus 1, that is 0 to 3. So now let's understand how to represent this maximum element that is possible and minimum element that is possible in binary form. Any number, let us consider 55. Now what would be its binary representation? First, you need to find the there are two methods to find its binary form. if you want to, I'm gonna do it by subtraction method. If you want to know how to find it by successive division method, then you can check out the link below. I will provide the links where you can understand the concept. For 55, by using subtraction method, you need to find the next greatest number which is less than the number itself as 55, greatest number less than 55, and which is a power which can be represented as a 2 to the power of something, like less than 55 and 2 to the power, what are the 2 to the power 1 is 2, 2 to the power 2 is 4, 3 is 8, 4 is 16, 5 is 32, 6 is 64. So we got this number greater than 55. So the greatest number less than 55 and is a and can be represented as in the form of 2 to the power something is 32. So here it would be 2 to the power 5 plus uh, 5 plus. Now, what is the number left? 55 minus 32, which is 3 and 23. So now we need to find the next greatest number possible, which is less than 23, and is can be represented in the form of 2 to the power something, which is 16. So 2 to the power 4, and now what is left? 23 minus 16 is equal to 3 plus 4, 7. 7. Now, similarly, in same fashion, we get 2 to the power 2. Then now 7 minus 4, which is equal to 3. Now 2 to the power 1. 2 to the power 0 is also here, which is equal to 1. This is 3. So we get now at 2 to the power 0. So we got it in this form. 55 can be represented in this form. So now to get the binary representation, you need to first consider here 2 to the power the greatest number itself 2 to the power 5. Then the next least would be 2 to the power 4. After that would be 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. In this representation of 55, 2 to the power 5 exists, so we'll write here 1. 2 to the power 4 exists, we'll write 1. 2 to the power 3 doesn't exist, so we'll write 0. 2 to the power 2 exists, we'll write 1. 2 to the 1 exists, 0 also exists. So binary representation of 55 is this one, 1 0 0 1 1 0. We can also confirm this. Let's confirm this. Binary or more 55. C is the same as, yep. So it's confirmed that this is method is right. Now let's move on to why I told you about this binary representation. N was equal, and in the first test case, n equal to and k equal to also 2. So each array, possible arrays could be of length 2 only. So and each elements can range from 0 to the power k minus 1. So if here k is small, so we could find it easily. To the power k, which was 0 to 3. Now the possible arrays could be 0, 3, 3, 0, 1, 2, 2, 1, then 2, 3, 3, 2. These are all the possible arrays which can be made from all these conditions. Now we also had one more condition that bitwise n. This is the all these arrays satisfies the first condition, but now for to satisfy the second condition, bitwise n of all its elements should be 0. So now let's first represent all these numbers in binary form. Now 0 is obviously 0 0, and 1 is 0 1, 2 is 1 0, 3 is 1 1. That's it. So for this array, let's see 0 and 3, which is equal to here 0 and 3. So 0 0 and 1 1. 0 0 1 1. So now to apply and press bitwise n operation, we consider it in the individual elements of this binary representation. Here is 0 and 1 result would be 0. 0 and 1 result would be 0. So we notice that if there is a 0, then the n bitwise n operation would always result in a 0. So uh, so this is true. This test case is this is a possible this satisfied the second test case also. Sum of elements should be as large as possible. Let's not consider this now. Sum is equal to 3. If it satisfies the first two conditions, then okay, let's move on. Let's check for 3 and 0. It will be the same since order does not matter over here. It would be just reversed there. So bitwise n of this would also result in 0. So this is also a valid array. Now for 1 and 2. 1 was 0 and 1, and 2 for binary representation of 2 is 1 0. 1 and 2, 0 1 and 1 0. It would give also 0, since 0 1 is 0 and 1 0 is also 0. So this is also true. Similarly, this would also be true. Now let's check for 2 and 3. 2 and for 2 it would be 1 0, and for it would be 1 1. This 2 would result in 0, but this 2 would result in 1, which is not equal to 0. So these two won't be a valid test case. So only these. So the answer would be 4. Now in the answer we also need to check. We need to divide and find, and the output should be the remainder of after division, and that means answer should be mod of 10 to the power 9 plus 7. But the answer would be same as the answer itself if it is less than 10 to the power 9 plus 7. 4 is less than 10 to the power 9 plus 7, so it would be the output itself. Now, if we go on for n equal to 3, k equal to 3, and so on, you would observe a pattern. Now, I can't keep on going and explain you all the possible test cases. So I will directly move on to the pattern that is observed in this problem. And that pattern is, let's consider n equal to m and k equal to x. Let's consider as y and x. So there are y number of uh, uh, the possible arrays should be of size y, and these elements should range between 0 to 2 to the power x minus 1. So in the previous example, we have observed that our binary representation of k equal to 2 had only two places to fill up. So it was 0, 0, 0, 1, 1, 0, 1, 1. Only two places for 0 to 1 to 2, comma 3. All these numbers could be represented by two binary numbers only. And let us consider for k equal to 5. 2 to the power 5 minus 1. 2 to the power 5 is 32 most probably. 4, 16, 32. Yes, it's 32 minus 1 equal to 31. Now you would now it is observed that a pattern emerges. This could be represented by five binary places. K was 5, and this could also be represented in 5 binary places. And since this is a max number, here also the max binary number that is possible is 1111. So if we now search binary form of 31, we would get this as the answer. Let's check. See, 5 1. This is a pattern that has been observed. So similarly, if we consider for 2 to the power 100, let's consider a smaller number. If k is equal to 7, 2 to the power 7 minus 1. So the max number that would be its limit minimum is 0 and max that is 2 to the power 7 minus 1. This is the max number. So this max number can be represented as a binary form of 7 digits where all digits are 1 to 4 to 7. So if we consider a general case where n equal to y and k equal to x, and only this is an array of size y, and these elements can range, as we have seen, it can range from 0 to 2 to the power k minus 1. That is, its binary form can be represented in x digits. Max mean can obviously mean can all digits would be 0, then it would be mean. All digits are 1, then it would be max. Uh, for this also, that there would be x. For this also, there would be x. Maximum x digit is possible over here. So now let us consider only for this array. We need to find more possible arrays of length y and fill with these and elements ranging from 0 to 2 to the power k minus 1. So only let's zoom in only at the one array. Let's take k equal to 6 here, and n equal to 5 over here. 1, 2, 3, 4, 5. 1, 2, 3, 4. Let's n equal to 6 also. Now n equal to 5. N equal to 5. We are now trying to understand the second condition. What was bitwise n of all its elements should be 0. So we know if any, this is one array. This is a 0th index, one first index, second index, third index, fourth index. This is one entire array of size 5. So that's why its index is last index is 4. So at index 1, if any, so to get the answer of all the bitwise n of all this to be 0, 0 needs to be in at least one of the, this is one possible case, 0 needs to be in at least one of the mm, positions. Any 1 0 should be over here, any 1 0 should be over here, any 1 0 should be over here, so that the bitwise n of all this, if all ones are over here, then still the answer would be 0. Finally answer would be 0. So this is the main trick over here, that we need to choose, we need to put 0 in at least one index, at least one position of each index. We need to put, and it should be distinct. If 0 is already put here, we shouldn't put 0 over here. Here third condition is also checked. If we put 0 here, sum would be minimum. We can at most can put 1 0 in all these positions. So now permutation and combination application comes in place. So if we need to put 1 0 in among all these positions, that is how many positions are 1, 2, 3, 4, 5, that is n equal to 5. Among 5 positions, we need to place only 1 0, so that it would be 5C1. If you have forgotten these concepts of PNC, I will put a link below. You can revisit that video and revise your concepts. For just remember this, for choosing we use combination, and for arrangement we use permutation. So we are choosing here, we need to choose one position where we will put 0. So we choose out of 5 position, we chose 1 0 over here. Similarly, we choose 1 0 from among all these 5 positions. We need to choose another 0 from all these 5 positions. It will be again 5C1 will come. Again we need to choose another 1 0 from these 5 positions. So another 5C1 will come, and it will go on k times. Since here this is of length, this is 5 and this is 6. So that, and if we 5C value of 5C1 is 5, this will come k times. That means k times, that means 5 to the power k and 5 here is n. So actually the answer is n to the power k. But here comes one problem. In Python, if you can do it in one line itself, directly the formula, print, this is the answer itself, print n to the power k. But since the test values of these could make it greater than 10 to the power 9 plus 7, so we need to, and they said that we need to divide it by, we need to mod it with by 10 to the power 9 plus 7. So if you do directly use this formula in Python, then you will get the answer. But in C++, uh, this is the formula actually. This is the one-line code in Python. Obviously, you need to use some more lines for inputting values and all. But the main logic is in one line. N star star n to the power k mod 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 10 to the power 9 plus 7. So in Python, it can be done in one line, but in C++, we need to use pow over here. Pow n comma k. And pow is of return type double. And for this test case itself, 10 to the power 20, oh no, not 10 to the power, 100,000, 100,000 to the power 20, this would give how much? 100. This is actually 5. This is 100, yeah. So pow does not, cannot return such a large value. So it will give an error. And, even if you try to do something with it, it will not give the right answer. So for C++ coder, they had to do something else. They had to manually write a loop and multiply each number. So this is the loop, answer equal to 1, and we need to use long over here. And use while k minus minus, answer equal to answer into n mod 007 3 4 5 6. Okay, anyway, you got the point. So what this does is, for first iteration, it would be 1 into n itself, and this would become n. For next iteration, this would be n into n. This would become n square, and this would go for n square into n cube till n to the power k times this while k minus minus. But we are using, we are directly doing this operation for each iteration. Now we can do this because the answer would be same if we even didn't do it. Like in the previous Python example, we the final answer is modulus. On the final answer, we use modulus operation. But even if we use like, let's take an example. If n is equal to 6, and this number, instead of this large number, 10 to the power 9 plus 7, let's consider this as consider x equal to 5. For 6 to the power 2, for 6 to the power 2, answer is 36. And if we use modulus 5 on it, answer would be 1. And for 6 also, 6 modulus 5, answer is still 1. Even if we use 6 to the power 3, answer would be 1. 216 mod 5 equal to 1. So what we observed here was answer won't change even if we use modulus operation on each iteration. And also, when we use modulus operation, the output of this operation would always be less than this number. Since if it is equal to this number, the output would be 1, output would be 0. And if it's greater than this number, then it will divide that number, like consider 1000008. And if we use modulus, then the answer will become 1. We will divide it. So the output will never increase than this number. So till some extent, the operation would happen normally, and the output would be the number itself. Since if it is less than 10 to the power 9 plus 7, after it crosses this number, then it would again come back to near to 0. So it will keep on cycling, and the final number will always be equal to the number which is generated by Python code, which is 222 6 to the power 7 32710. I hope you have understood the problem and my solution. If you still have any doubts, comment down below. I will try to solve it.